We're going to spend this lesson practicing our graphing skills while also discussing continuity and domain range. So to be honest, there's nothing new in this video. These are all skills we've been developing over the last couple of lessons. So my suggestion here is you pause as much as possible, try examples yourself, check back in as necessary and see how you're doing. Okay, so we're going to start by sketching. Sketch this function, then state domain range. So we're going to make the same old list as always. Before you start, you probably want to factor the top. Can't really factor the bottom because it's good the way it is. And we'll make our list. So our zeros come from the top. We have 2 of them. -1, +1. We'll put those in as we go here. We always want our y-intercept. So we're going to put 0 in for all of our x's. The x's will disappear. You'll have -1/2. There's our y-intercept. Vertical asymptote comes from the bottom. X equals -2. Okay. Thinking about our horizontal asymptote next. So the largest power of x that I see is my one on the top. So if I think about that as x squared is my biggest power, I've got I have 1x squared on the top, but no x squared on the bottom, which tells me there's no horizontal asymptote. This is an oblique asymptote question. And to do oblique, we got to do some long division. So x squared, there's no x's, so put your placeholder in. -1 divided by x plus 2. We need to multiply by x. We've got x squared plus 2x's. Subtract. Okay, turn an x by multiplying by -2. You could just stop there because that's all we really need. But to show the math, our remainder of 3. This is all we really care about. That's our oblique asymptote. So y equals x minus 2. So we're going to start at -2. And we have a slope of 1/1. So we'll make a couple of dots. We'll turn those into lines so it becomes an oblique asymptote, not just dots. And we have to check for crossing as usual. So our oblique asymptote is x minus 2. Our initial equation was x squared minus 1 over x plus 2. We're going to cross multiply here. So 1 times stuff makes stuff. I want to go the other direction. If you need to, write out that what you're doing is you're foiling. And if we foil, we end up with some nice things canceling each other out. X squared, positive 2x, negative 2x, leaving us with -1 does not equal -4, so no cross. Okay, we can draw our picture in now. To draw our picture in, we have to approach asymptotes and go through zeros, or go through dots, I should say. So there's one part. Because we shut out the top, the next part has to start at the bottom of the asymptote, the vertical one. So it's going to be somewhere down here. And that would be a great picture. This question wanted one more thing, though. It said in the picture, or in the statement, state the domain range. Now, one of these is easy, one not so much. So, domain. Let's do the easy one first. It's always all real numbers for functions. They go left and right forever and ever and ever. However, we have a vertical asymptote, which we don't touch. So we can say that x is all the numbers except for -2. Range is the tricky one. Range is actually made up of 2 separate parts because our graph is literally made up of 2 separate vertical parts. The top part, I call this one number 1 up here, comes down as low as your y-intercept, as low as that point right there, which is what, -1/2. So we know that y has to be all the numbers, and it has to be bigger than -1/2. And it actually touches it, so I have an equal sign in there. However, this other part down here, first of all, I've graphed it roughly. I don't know exactly where it is, and I kind of need to because my graph never gets above whatever that point is. If I don't know that point, I can't really put the other part of this in. I know my y value has to be less than it, but I don't know what it is. So here is where our technology comes into play. When you're graphing something like this, we can always use technology to check it, but we also sometimes need it to actually get our graph in exactly the right spot. So we're going to go to our y equals screen. Using brackets, we're going to put in x squared minus 1 on the top. We need the brackets so it does what we want it to do. And on the bottom, another set of brackets, x plus 2. If you graph it, hopefully it matches what our picture looks like, and it does. Okay. What I really need is I need the local maximum, if you will, right here. So to get that, I'm going to go to my calc menu. I'm going to do number 4, the maximum. This is where that left bound, right bound stuff comes in. A little bit hard to tell because the cursor is going to be where the words are. So the cursor is actually right there right now. If I go to the left, notice my y values are actually going down. So I feel like I'm in a good spot for my y values. I can go to the right hand side, so I have to go up and then back down again. I'm going to take my guess. It looks to me like negative 7.46 is the y part of that vertex. Why did I want that? I needed to know how high my graph got. It never gets above negative 7.46 in that section. If you don't like using inequality notation, I'm okay if you guys use bracket notation too. Nothing wrong with that. Just make sure this would be a square to infinity or negative infinity up to negative 7.46 a square. And you can put a comma between them, or you can use your and symbol. Okay. That one's a graphing calculator question. There's no choice on it. You kind of have to use a graphing calculator on IB exams or questions that you literally, there's the only way you can do them. You can't do them by hand. They have to be graphing calculators. You might as well get used to using that from time to time. Okay, the other ones, you won't need them, but if you want to use a calculator to test it out, see if you got it in the right spot, go for it. Okay, you guys try this one. Exact same idea, same questions. Graph it, domain range for me. Okay, start off by, I don't know, factoring. X minus 2, x plus 2, bottom x plus 2. Oh, that's nice, because I can cancel, leaving me with just the function x minus 2. This is what I'm graphing. Now that's just a line. That line has a y-intercept of negative 2 and a slope of 1 over 1. That's really nice to graph, really quick to graph. Negative 2 and an up 1 over 1, up 1 over 1, so on, so on, so on. The only trick to this line is because we canceled something out, we have ourselves a hole. The hole is at negative 2, and whatever you get when you put negative 2 in for x. So how about negative 4? Negative 2, negative 4 is right there. I'm going to make it a dot, but an open dot. And now I have my line, my rest of my line with my hole in the middle. We can do domain range pretty quickly for this one. Domain is going to be all the numbers, because lines go left and right forever and ever and ever, except where the hole is, because at the hole the graph does not exist. Okay. Range, same idea, goes up forever, down forever, but at the hole, the y part doesn't exist. There's our graph. Okay. You guys can try one more for me. Okay, pause it, try it, see what you can do. Let's factor the top. Let's factor the bottom. Ooh, I got myself a hole because I'm canceling. I'm left with x plus 2 and x minus 1. That's what we're going to be graphing, okay? So my list is coming off of that list. So what do I need? I need zeros. That's negative 2. That's right there. I need a y-intercept. And I'll get 2 over negative 1, or in other words, negative 2. It's right there. We'll have a vertical asymptote. That's 1. That's right here. We'll have a horizontal asymptote. The largest power of x that I see is just one x on top and one on the bottom, so 1 over 1, or just 1. We'll test that for a crossing. 1 over 1 equals x plus 2 and x minus 1. I like this one because stuff and stuff. And 1 does not equal 2, so no crossing. Just a regular old horizontal asymptote. Okay, we can draw this in there. Oh wait, there's one more piece of information, wasn't there? There was a hole. I forgot about that. So let's go to our hole. The hole is at, we crossed off the -1. If you put -1 in for x and -1 for x, you'll get +1 on the top and -2 on the bottom, or -1/2 if you will. So -1 and -1/2 is right about there. So here's our graph. Approach the asymptote, go through the dots, including the hole. Okay, shot at the bottom, so start at the top. There's no mirrors to worry about. There is your graph. Okay, domain range, sure we can do that. Left forever, right forever, except it didn't exist at the hole or the asymptote. Same thing for your range. It didn't exist at the hole, which was at -1/2, or the asymptote. So this one has 2 breaks in the graph, left and right, and also up and down. The only ones you really have to worry about are the ones that have oblique asymptotes for maxes and mins, because those create the kind of diagonal parabolas, if you will. Okay, just some words for us. So we even call them holes and asymptotes. The technical term for these discontinuities are, well, if it's a vertical asymptote, we actually call that a infinite discontinuity, because you're approaching infinity. You're going straight up forever and ever and ever, straight down forever and ever and ever. Okay, so we call that an infinite discontinuity, in case you ever come across that. We also have things that we call point discontinuities. There's a point missing, aka a hole. Okay, just so we have the language that goes with this. Now, one of these we can actually get rid of. You can actually get rid of a point discontinuity. You can do that by creating a piecewise function. So I'm going to show you one of those. So let's say this is my graph. This is called a piecewise function. It's made up of 2 pieces. One of the pieces, the top one, we've actually done before. That's this guy. Okay. We factored it earlier. It's the same question as before. And x plus 2. And they canceled. And it made a line that looked like, starts at -2, like that. And had a hole at -2 and -4. This is the second one we did. Okay, that's what the first part of the graph says. It says do this graph except for at -2. At -2, it wants us to make this graph. What that means is it wants you to make a dot at -2 and -4. In other words, it wants you to color in the hole. And now we've removed that point discontinuity by defining its value at that point. Okay, so you can remove one type of discontinuity. Can't get rid of an asymptote. That doesn't exist. An asymptote's an asymptote because you can't divide by 0. But you can always remove a hole if you want to do it. Okay, that's it. Those are our graphs. Okay, hopefully we're getting pretty good at graphing by this point. We've got one more lesson left about solving some stuff. We're going to use graphs to do that at some point. But if you're stuck, come see me, send me some questions, and I'll help you out.